Okay, so there are lots of transformations that we can define from one space into another space. Not all of them can be represented with matrices, but let's define a very special type of transformation T that maps from Rn into Rm. And so we're going to say that transformations T are called linear transformations if they satisfy two properties. The first is we can break up addition inside the map. So in other words, if I want to find out what is the image of the vector u plus b, I can calculate the image of u, I can calculate the image of vector v, and then add those two together. So applying the transformation to vector u plus v is the same thing as applying the transformation to u, and then adding to that what we get when we apply the transformations to v. And this needs to be true for all possible pairs of vectors u and v in the domain, which is Rn. So if this works for some, but not all, then the map is not linear transformation. But if this works for any pair of vectors in Rn, then that's the first property. Property number 2 says that we should be able to pull out scalar multiplication. So in other words, the transformation of scalar c times vector u is equal to scalar c times the transformation of u. And this also needs to be true for all scalars c in all vectors u in the domain, which is Rn. Okay, so more succinctly, we would say that a transformation T is a linear transformation if we can break up addition and if we can pull out scalar multiplication. And this leads to a very nice theorem that says every matrix transformation is a linear transformation. And we'll take a look at the converse of this statement, namely, can we write any linear transformation as a matrix transformation? But for now, we're going just in one direction. If I have a matrix transformation, so T is mapping from Rn into Rm, and this mapping T of x is defined as multiply matrix A times vector x. So why would a matrix transformation like this satisfy the properties for a linear transformation? So the first property is we would like to show that T of u plus v, which in this case would be multiply the matrix A times the sum u plus v. And from properties of matrix vector multiplication, we've proven that this does break up into A times u plus matrix A times vector v. And this is exactly how we would define the image of u under transformation T plus the image of v under transformation T. So this property, breaking up sums, this follows directly from the property of matrix vector multiplication. And very similarly, if I want to prove the second property, which is what would the image of scalar c times vector u look like? Well, we're defining this map as matrix A times c times vector u, and we have also shown a property of matrix multiplication that we can pull that scalar out in front. So we can first take matrix A and multiply it by vector u, and then multiply by scalar c. And this is exactly the same thing as taking scalar c times T of u. So any matrix transformation is going to be a linear transformation. Okay, now let's take a look at a theorem relating to linear transformation. So let's consider transformation T mapping from Rn into Rm is a linear map. Then it's going to follow that when I apply this transformation to the zero vector, and keep in mind here we may actually have two different zero vectors. So this one sits in the domain, which is Rn. So that is a vector with n zeros. And we're mapping to Rm. So this zero vector lives in Rm. So the number of entries in these vectors may not be the same, but both of these vectors contain all 0 entries. So what we're saying here is that the image of the 0 vector in Rn is going to wind up being mapped to the 0 vector in the codomain, which is Rm. So let's take a look at why this is true. We'll do the proof down below. So let's first define a vector v, which is going to be in our domain, which is going to be in Rn. And we're going to define that the image of v, when I apply transformation t to v, I get some vector b, which is in the codomain Rm. So let's consider the following map. What happens when what's the image under map t of the vector v plus the 0 vector? Well, since this is a linear map, t is a linear map, we can break up the addition. So that's going to be t of v plus t of 0. And t of v we defined as the vector b. And t of 0, well, we don't know what that is, so we'll just call it t of 0. So on the one hand, taking the transformation t and applying it to vector v plus 0 gives me the image of v, which is vector b, plus the image of 0, which we don't know just yet. So since this vector v plus vector 0, by definition of 0 vector, gives me the vector v, then another way that I can think about this is the transformation of v plus 0. Let me first add these two vectors. That's going to equal t of v, which equals b. So now I know that t of v plus 0 is equal to b, and t of v plus 0 is equal to b plus t of 0. So these two quantities, b plus t of 0, has to equal b. And the only vector that I can add to b and wind up with b is the 0 vector itself, by definition of the 0 vector. So therefore, we see that t of 0 must equal the 0 vector. And now this 0 vector is sitting in Rm. So that's the conclusion of our proof. If t is a linear map, then we know for any linear map, the image of the 0 vector in the domain needs to get mapped to the 0 vector in the codomain.